All right, if you've studied inverse functions before or watched the previous video, um, I mentioned that we would now talk about inverse functions and their graphs. So first of all, let's remind ourselves how to find an inverse function. The quickest way to find an inverse function is just to think about how do we reverse a function. So thinking about our inputs becoming our outputs and our output becoming our input. I'm going to switch x and y. Then I want to solve for y. I want to construct this function so that it's reversing everything we're doing. So I'm going to say add 4 to both sides. And then if I finally divide by 3, I will end up with x plus 4 divided by 3 over on the left side, which is equal to y. So I'm just going to flip that around real quick, which is the same thing as 1/3 x plus 4/3. Now I can do the same thing for just a coordinate point. Its inverse will just be literally switching x and y. And finally, f of x, remember, think of that as y as well. So I'm just going to call this x, again, equals y to the third plus 2. So x minus 2 will equal y to the third, and y would be equal to the third root of x minus 2. Or if I replace y again back to f inverse, now that I've reversed everything, the inverse function of the original will be equal to the third root of x minus 2. Now, if we think about their graphs, the top one is probably fairly easy, considering that we get -4 with a slope of 3. I'm just going to start at -4 and plot points up 3, right 1, thus constructing a nice straight line between my points. Well, if we do that same thing with our other points, so with our inverse function, I'm going to start at 4/3. What used to be my x-intercept at 4/3 is now my y-intercept, and I have a slope of 1/3 rather than a slope of 3. So I'm going to go up 1 from there and write 3 units and essentially construct a nice straight line through those points as well. So making a nice straight line through my points. Now it's a little bit tough to tell, but maybe if we construct our other lines in the same fashion, so going 3, -4, and then our inverse point at -4, 3, it might be a little easier to spot the relationship. What's the relationship between the original graph, such as down here where we would be up 2 units, and then if I plug in some more points, plug in 1, I get 3, plug in 4, or sorry, plug in 2, I'm going to get 10, so it's going to just kind of shoot upwards here, as well as going downwards very quickly. Remember, cubic functions are that nice S-curve going on. Well, what's the relationship between that and a cubed root function? And we can pop that into our calculator if we wanted to, and we would quickly notice, if you did, and feel free to pause the video and try it, but if you did, you're going to notice you're going to get an S-curve heading out this direction. And the relationship that we find out between all of these functions is that the new graph is just the reflection of the old graph over y equals x over that diagonal line, y equals x here, that blue line I just drew on the graphs. Notice they all reflect. This x-intercept became the y-intercept. If you're right on the line, it doesn't go anywhere. Our points just reflected right over the top of that line. And it really illustrates it with those curved lines. It's easy to see that symmetry over the blue line. Now, the reason we bring that up is it has huge ties into whether or not something will have an inverse function or not. And that's the real key to this lesson. If I want to graph f of x and know if it has an inverse function without graphing f inverse, or without even finding f inverse, what I can do is think graphically. It's going to reflect over that line y equals x. So right now my parabola, notice the x squared, so I'm going to be down at -2. Then if I plugged in 1, I would actually get -1.5. Or if you remember our old rule, going up 1/2, 3/2, 5/2, 7/2, we're going to kind of shoot up this direction. Well, notice we'll do the same thing the other direction. So it's going to kind of shoot down this way, and we'll get that nice parabola. Well, if we reflect that over the line y equals x right through this diagonal line, Well, remember, horizontal lines become vertical, and vertical lines, or parabolas that rise, are all of a sudden now going to rise out to the side like this, right? And do the same thing again the other direction. It's also going to drop this direction. And the problem is that blue line now doesn't pass the vertical line test. It's no longer a function. So graphing the original function, that red line, can quickly tell us if it'll have an inverse, whether or not it passes the horizontal line test. Because I could draw a horizontal line on my graph that would cross my red line in two different spots. I know that its inverse function, the blue line that we drew, won't have an inverse, or it won't be a function. So in order for a function to have an inverse function, again, the original function, my red line here, needs to pass the horizontal line test. It can't be intersected in two spots by any particular horizontal line. Right? Otherwise, each input, right, though every input already had one output, every output right now, note that y equals 4, has two different inputs. It would not have an inverse function. Again, algebraically, how would that show up? Does every input have only one output? Well, if we did find its inverse here, again, I would switch x and y. X would equal 1/2 y squared minus 2. I'm going to add my 2, and at the same time, then also multiply by 2 to get rid of this half. 2x plus 4 equals y squared, and the real key comes at the end. Y will be equal to the square root of 2x plus 4. But remember, anytime you take the square root of both sides, you also have to say plus or minus. Because every number I plug in now will both have a positive and negative answer, assuming we get an answer at all, that's not a function. Every input can't have more than one output. So not a function. The purple graph or the purple equation wouldn't pass a vertical line test because the original, again, didn't pass the horizontal line test. So taking a look at a few different examples, we've studied functions that look like all of these. Which ones of these would have inverse functions? Again, the hint is it depends on the horizontal line test. Oops, and I got a little typo there. Note that they should be spelled correctly, but anyway. So we could check our horizontal line test. A linear function obviously will pass the horizontal line test, so it will always have, yes, it passed the HLT, the horizontal line test, it'll have an inverse function. As we just looked at, parabolas, on the other hand, will not. They're going to cross in two different spots, so no, due to, again, the horizontal line test. Both of the functions at the bottom are cubic functions. We've studied those before. This function does pass the horizontal line test because notice the little curve in our cubic function isn't severe enough to have a problem. But in this one, there's a whole lot of spots in here, right where I left the red line, namely, where we not only crossed twice, we crossed 3 times. So again, no. Now, does that mean that parabolas can't have, or cubic functions can't have inverse functions? No, it doesn't. All it means is we need to restrict their domains. So if we think about it, on this parabola with a vertex at 2, -9, if I restricted the domain to just be from the vertex and to the right, what if we look at this kind of like a piecewise function? What if I don't look at the whole graph? What if I only look at that blue part? Well, let's just make sure that as long as x is greater than or equal to 2, I start at 2 here, and only go right, well then it would pass a horizontal line test. You can imagine I'm not going to run into two different spots. So at the same time, I could do the same thing. What if I only looked at the left side? What if I only look at this red portion here, right? Or I said x is less than or equal to 2. The red part alone also is going to pass my horizontal line test. I'm only ever going to run into that red line in one spot. Same thing goes for my cubic function. If you think about from these maximum and minimum points here, well, from -1 and to the left, right, traveling down this way, as long as x is less than or equal to -1, I should be okay. Same thing goes in the blue. If I only traveled to the right of this portion, what if x was only greater than or equal to 1? I should be okay. And finally, I could even do just this little curve in the middle. What if I let x exist between -1 and 1? As long as it only exists on that green line, a horizontal line will only ever pass it once. That works. All of those would be good ways to restrict the domain to create an inverse function. So our final thought is, if you did have a parabola, if you do have a quadratic like x squared, a function that would normally be graphed at 1 and 4 here, going this way, and also traveling up through 1 and 4 this direction, repeated outputs, normally we would say it didn't have an inverse function. But notice we've restricted the domain. We've said that x is greater than or equal to 0. So I only actually want the right side of that graph. Now it passes the inverse, or passes, sorry, the horizontal line test. It has an inverse function. So I could now go ahead and find that by saying, well, x equals y squared. Y would be equal to plus or minus the square root of x. But because of my restricted domain, this now becomes my range. That's the new range. And my outputs can only be greater than 0. So f inverse of x would be the square root of x, but only the positive portion, thus creating an inverse function. If you graph that new function, graph the square root of x on your calculator, you would quickly find out, again, just switching x and y, it's going to go out this way, and that passes a vertical line test. Again, I hope that helps you understand inverses and their graphs, and why sometimes we're going to see a restricted domain, because if a function previously didn't pass the horizontal line test, if we restrict its domain, it can pass now, thus creating an inverse function. Have a great day, and good luck with inverses.